Okay, yesterday I was talking a lot, and we started talking about symmetries and asymmetries, and why not every configuration uh, why not every configuration of charge, partial charge, is possible in nature. Um, I had been talking for 1 hour and a half, and I ended up sort of talking about how positrons and electrons might annihilate if you look at them from a classical perspective as ring currents that have a magnetic field, and that magnetic field lines up or doesn't line up just before they go and literally sit on top of each other. Um, I want to go back to that topic because it's a very interesting one. I think the topic of antimatter, what antimatter is. Everybody knows what it is, but how matter and antimatter annihilate exactly, and where does the charge go? Can charge really vanish and become real photons, electromagnetic fields, and vice versa? Can photons, real photons, not virtual photons, sort of somehow disintegrate into opposite charges, a positron and an electron? So my point of view is that it's not possible. Charge does not get lost, and with all respect for Dirac, I think he sort of neglected the fact that energy is indeed charge in motion, but charges don't vanish. So I want to do that by actually going back to a discussion I had on ResearchGate on that, which was not very conclusive. In the end, I gave my opponent, I would say, the benefit of doubt. He presented this picture of a bubble chamber, a rather famous bubble chamber experiment in the bubble chamber of Fermilab at the time. That bubble chamber has now been decommissioned, well, a long time ago. It was the 15-foot, 4.52 meter cryogenic bubble chamber, which was used to see what happens when you fire a beam of protons into this chamber filled with hydrogen or heavy neon or a combination. I will talk about do. And this is a picture where my opponent in that discussion claims, like, look, this is a conclusive proof that a real photon can actually disintegrate into a positron and an electron. We are looking at this thing here. So the claim is basically what you see happening is that at this point B, suddenly we have two charged particles, an electron and a positron, presumably. How can we know that? Well, they have a certain energy and there's a magnetic field. And so because they are charged, they will, depending on their positive or negative charge, either move, in this direction, follow an orbital like this. And then as they lose kinetic energy, the tangent in which they move becomes sharper, and so they spiral then into a tighter spiral, and then at some point in time, if it's a positron, it will annihilate back with another electron in some electron shell of the hydrogen, or and for the same is for the electron. It will be captured by an ionized hydrogen atom that wants to complete the electron shell, or other things will happen to it. Yeah, it's quite chaotic situation. What you can see here, let me explain it, is so we have this bubble chamber. Let me also say, to make sure that these things are well understood, and also to bring home the point that it's not always easy to assume this or that is happening. This bubble chamber, I said, there's been experiments with a bubble chamber filled with hydrogen, So yeah, to explain a bubble chamber, what basically is a bubble chamber? It's a gas but cooled in liquid condition, but just below or at the boiling point, actually. But there's a lot of pressure on the bubble chamber, so it doesn't boil. What happens is just before they send the beam in, a beam of particles, you can see from the tracks that this beam came from here, because all the tracks lead back. Just before they send this particle beam in, there's a piston that decompresses the chamber a little bit, and so the charged particles will rip electrons from the electron shells of the hydrogen, or in this case it was a combination of hydrogen and heavy neon. I will say why the heavy neon is important in a moment, or might be important. And so it's like the bubbles you see in a beer glass. There's a process where these charged particles indeed sort of create little bubbles because they boil. The track is basically the trace of where the liquid gas is boiling, and so it forms very small bubbles that become larger as more and more the bubbles grow in size as sort of cooks. And then a picture is taken, and you can see these traces. That's all kind of standard, you will say, and I'm sorry if I bore you with that. But I think it's important to sort of see what happens. So what we have is actually, and this is special about it, is that we have such a trace of a charged particle, which presumably is a positron based on the positive charge it must have, because the negative particles they go in another direction. What is interesting about this event in B, because there's other events where an electron and a positron pair, a matter-antimatter pair are created, like this here, and this presumably also comes from some kind of particle you cannot see, a photon or a neutral particle, because neutral particles, when they have enough kinetic energy, small, they don't sort of have enough energy to do something with these nuclei of or the electrons in what we have here, this mix of hydrogen atoms, H2. They come in, it's a gas that comes in a molecule with two atoms, and the heavy neon with an atomic number, I stress that, of 10 and an atomic weight of 22. So that means basically you have 10 protons and 12 neutrons. So I'm just saying that because this liquid is dense, and so there's plenty of room for the particles that come in to interact, and all kinds of funny things can happen. And so saying what he does, and here I come to the point, is saying his claim is, look, this is proof that a real photon, a heavily a highly energetic photon can be created first from pair annihilation. So his thesis is basically that we have a positron here, and that hits at this point A an electron from probably not a free electron, but an electron in either a neon shell or a hydrogen shell. A hydrogen shell is simpler, that's only one electron. But so in that mix, that heavy liquid, what happens is, he says basically, standard theory has it that this annihilation of a positron and an electron here at point A will produce a photon, and that photon travels, and we can't see it because a photon is neutral, travels at the speed of light, and here at point B it disintegrates into a matter-antimatter pair. I did not insist in the discussion, but there's several issues I have with his argument. First is that the standard process for these are all the modes in which an electron can meet a positron and annihilate. Usually you will have 2 photons, and these photons will go in opposite direction because there's conservation of linear and angular momentum. And so you don't have just one photon. And so here, I don't say this suggests that there's only one photon, but it sort of suggests, because these photons go in opposite direction, that the other photon goes straight back from where the positron came. And that would be weird for me. So that's where I'm thinking, like, you don't have conservation then of this positron. Its linear momentum is clearly headed this way. So if it did disintegrate into if it met an electron and it integrated, then probably you have something more like a particle here, a virtual neutral particle, because indeed it doesn't create bubbles. And that sort of disintegrated then into something. What kind of particle? I'm going to talk about that now. That could be I don't like to say it's an intermediate vector boson, because when I talk about virtual particles, I think not necessarily in terms of quarks and gluons and Z0 and W plus minus bosons, but it could be a virtual particle, and I'm not skeptical about that possibility. I will come back to it. But for me, saying that we have here pair annihilation, and then a photon. Let me put it like this. Sorry, a photon. That's the usual standard thing to represent a photon, a wobbly line, and that disintegrated then, and this is the proof that one photon can disintegrate into an electron and a positron, and the photon will be a real photon. It will not carry charge. I will talk about virtual photons in a moment. Difference between real and virtual photons is that virtual photons might be, I'm not saying they are, but many academics would think that virtual photons might exist, but they might actually carry the positive and the negative charge in a way that both are sort of in a zero energy. I will talk about that later. But so at point B is this is what I'm saying here. This hypothesis that we have a real photon, disintegrating into an electron-positron pair. I'm thinking, well, maybe that proof is not conclusive, or this picture is not conclusive. To sort of drive the point home, I will explain exactly what happens in this experiment. I looked it up as much as I could to sort of see what is it really. Is it a proton beam that comes in, or an anti-proton beam, or some heavy nuclei that are sent in? And the answer to that is that the Fermilab is connected to the to an accelerator, the Tevatron accelerator, and that produces basically proton beams. And these proton beams, protons are the nuclei of hydrogen, so they're relatively easy to produce. From these protons, you can, if you fire them onto an iridium target or something else, then you can produce antiprotons. So these are that's a two-step process. I will talk about that. Antimatter is not, we live in a matter world. The antimatter that we see is, nature produces it. I will show that maybe now. Here. Oh, let me select that one. Yeah. In the atmosphere, protons come in. I said these are hydrogen nuclei. A proton is just a hydrogen nucleus. And, they come from the sun. We live in a matter universe. And they hit the atmosphere and they collide with an atmospheric molecule. Can I... No, I can't fix it. In any case, they collide with an atmospheric molecule, and then you have these beams, these jets of no, a jet basically, not a beam of what is called pions. Let me bring it back here. Well, no. Pions. Pions are unstable particles. It's actually kind of funny. We call a pion a positively charged pion also a pion, and a neutral one we call it a pion, and a negatively charged pion. But these have very different lifetimes and masses and all that, and so their own disintegration back into sort of more stable constituents is a bit complicated. The negatively charged pion will become a mu1 electron. You see that here, a mu minus. The positively charged pion becomes a positively charged muon, and that actually disintegrates. Muons are like heavy electrons or heavy positrons, and they emit a neutrino, and they become in the end, what you see at the bottom here, electrons and positrons, electrons and positron pairs. So the question of antimatter, how it's produced, I would say artificially, both by nature. These protons that hit, it's like they come with enormous in energy, and this is the energy that we recreate in accelerator systems. But they are created by matter, elementary matter particles, protons, or electrons in other processes, hitting the nucleus of other composite or more complicated atoms or molecules, but matter molecules. And then these the antimatter we see is highly unstable because it will annihilate with ordinary matter. So to go back to where we were. So that's what happens basically. There was a beam of protons. It's like a 2 or 3 stage process that hits a production target. I don't know what material. In that process, and this is the wonderful technology of these things, is that neutrinos get ejected, and apparently they can create then a neutrino beam. And so it's this neutrino beam, highly energetic neutrinos, muon neutrinos, because there's these electron neutrinos which are very light and were easy to detect. In the second generation were much heavier neutrinos, so much more energetic. They can take away a lot more energy, so that comes in handy in these high energy processes. And then you have tau neutrinos that were discovered even later, the third generation. But these are very highly energetic particles, I would say, light particles, because they're neutrinos, in the 70 to 80 giga electron volt range. That's enormous, because the electrons and protons and their rest mass is in the mega electron volt range, 0.511 for an electron and a positron. So giga electron volt is huge, and it's all kinetic energy because neutrinos are not supposed to have any rest mass. So in any case, so you have this enormous beam of neutrinos really coming in and then creating this shower of these jets. Of what did they create? Apparently, indeed, like just when a proton, a highly kinetic proton hits an atmospheric molecule, they produce pions, plus, minus, or 0, and rho mesons, and maybe also omega mesons. I don't know, these rho mesons and omega mesons are like, also sort of a second or third generation, whatever you want to call it, even more unstable with more energy, which means more mass, and that means that they disintegrate very quickly into other lighter unstable particles like pions. So in the end, the whole production process that you see here is basically probably, I don't know, I didn't study it in detail. I really just want to give you a feel for the conversation I had with this guy. Say, okay, the end result is that you have these particles, pions. So here even I'm not sure, is this, is it really a positron or is it a positively charged pion? He claims, and I must assume he's right, it's a positron. That's quite possible. Probably there is some process here before. Ah, yeah, here actually, when we trace that beam back, you know, you see it actually results itself from, you know, some kind of disintegration of something into something positively charged, negatively charged. Then there's a weird other particle here. I don't know, or maybe this is a separate thing. Actually, there's a jet of four things here. 1, 2, 3, 4. Okay, that makes sense. So we would have two negatively charged electrons. Let's assume that, and then one positron here and one positron there. Here's and then because of the different kinetic energy, this one, you know, this must have lower kinetic energy because it sort of, you know, gets a lot more. It gets deviated from its trajectory much more rapidly than this one. So yes, let's presume that that would be compatible with the you know, the disintegration process of a neutral pion, which usually, you know, disintegrates into gamma rays. But these gamma rays, again, are they real photons, or more likely, you know, photons that disintegrate into, you know, positron and electron pairs? The usually, you know, the end of the whole, after whole circuit, I said disintegration, you know, first it's going to be like two photons, but I think they're virtual photons. The end result of a neutral pion, and I go back to my you know, what nature produces here. A neutral pion will disintegrate in two electron positron pairs through this intermediary process of what are referred to as two photons, but I think these are more like virtual particles. The charge is in total 0, but I'll explain how these might actually carry the neutral and a positive charge without us noticing, in a very classical argument that I will develop in a moment. So this thing, two photons, as you can see in nature, these are not normal photons. These are photons that disintegrate into what you have here. So that's likely what happened. Two positrons, two electrons, and one then endpoint A disintegrating, no, actually hitting an electron, a positron hitting an electron, and producing some photon, which I think of as a virtual particle. Let me show you what I think happens, and this is my theory, my crazy crackpot theory, or not so crazy crackpot theory. You know that we think of in our classical interpretation of quantum physics, we think the mistake is that, you know, electrons and positrons, you know, they have a structure. They carry charge, and they have a zero rest mass, and we think that charge, you know, is sort of a tiny ring current superconducting loop, as we call it, the smallest superconducting loop. Well, maybe the proton and the antiproton are the smallest ones. They go round and round and round, and I explained that in previous lectures. This motion of the charge, that's basically creates and gives the positron and the electron an electromagnetic mass that is equal to, you know, what you understand by the mass of an electron at rest, 0.511 mega electron volt. And because of that, we know that it explains, this model explains why an electron and a positron have a magnetic field, which we drew here, the field lines of the magnetic field of our positron and the magnetic field lines of you know, our electron. And so there's a north and a south. And we think that in most cases, when an electron and a positron, they attract each other because positive and negative attract each other. They will also line up what tiny little magnets do. They will be in this dance. Maybe they form an unstable, actually in most cases they do, positronium it's called. A tiny moment where, these electron and positron sort of sits on top of each other, but doesn't sort of immediately create what we have here, two photons that absorb all the energy and all the force of this collision. This is a classical Feynman diagram. So what I think happens is basically, if we want to see where the energy goes, and you think about conservation of energy and momentum, also linear and angular. I know this looks chaotic, and this is where I sort of ended my last lecture. Is you can think of the force on the positron, the force on the positron, and that will have two components. One is the electric field multiplied by the charge of the positron, and that gives you, according to law, the electric force. Okay, and we know that for the force, when you have two things that attract each other, you have force here, and the other force, Lorentz force, will be opposite. Let me draw the arrow. We're talking vectors. So then we have the magnetic force here. Again, the positive elementary charge times, well, I can't explain everything again, the velocity times the magnetic field vector. We have the magnetic field vector, and a force always acts on a charge. So this is something also that you should remember. We can add forces. There's a lot of adding of amplitudes, but we will add forces here in a classical approach. Times the velocity, which is c, because we think of that tiny little Zitterbewegung charge, as we call it, rotating around at the speed of light. We developed our model. Let me repeat it. So we have a tangential velocity that is equal to the radius times the angular frequency. And then we interpret c, we have E as mc square, right? And then we have the Planck-Einstein relation. So this A times A must be equal to C divided by the angular frequency. We know that angular frequency is the energy divided by hc, and then we can replace well, that's it actually. We have the Compton radius, the real radius, measured radius of an electron given by hc divided by E, and we can write that as we know the energy is mc square times the c that falls away. So we have our Compton radius, which you can find in textbook, h bar divided by mc. Very simple model, and I think that's why I sort of insist on also interpreting electron-positron annihilation in such a classical way. So let's go to the force, the opposite force on the electron. So there we have, and here I messed everything up, we have minus with the electric field vector, the electrostatic attraction, the electric field is opposite, so we have a minus there. For the magnetic field vector, we don't have a minus, but the velocities, a positron behaves like an electron, except that its spin or angular momentum or magnetic moment will be up in one direction. And if for the electron it's in the same direction, we know that the positron, the charge must go in must go in the opposite direction. So for the electron, it spins in this direction. For the positron, it spins in that direction. So we have a minus V here, but again, the charge is minus, so that's where all these pluses came then from, right? And then we think it's very simple. We can add these forces, and that's where things, I think, conceptually go wrong a bit. We have the charge positive charge of a positron, and we think that the negative of the negative elementary charge is the same. QE plus is equal to minus elementary charge minus. This is the reasoning, right? If you do that, yeah, you get this formula that we have the force that is twice the force on the positron, or twice the force on the electron, and that's kind of nice, because then you can say, yeah, so the energies must be added, because we can add the forces, and energy is force over some distance, and then yeah, this force. That's the other problem I have with, this disintegrating into a photon. The electron and the positron coming together, they're sort of the linear momentum bomb comes to a grinding halt, but it must go somewhere, so it goes here in a photon, and it goes there in a photon. My thing is, well, we're actually adding forces, not fields here. We have the fields, but here we're really adding forces. A force must act on a charge. Where is the charge? And the theory in mainstream theories, well, it just vanishes. Charges become fields. They become these photons. And I'm going like, no, maybe not. Maybe they become what they discovered in the 70s, this theory of intermediate vector bosons. They are like photons, but they have a lot more mass, no zero rest mass. Or maybe they have zero rest mass. Actually, they do. So I'm thinking these photons that we have might be, these kind of intermediate vector bosons that, as said, can be neutral, the Z0 boson, but they can also be positive or negative. So maybe there's a photon, not a photon, but a W plus boson and a W minus boson, or maybe there's a Z0 boson. And here we have maybe a real photon then that takes all the field with it. I don't know. There's very ways of combining. Here I assume that the spin is lined up. So the magnets, but maybe their spin is opposite, and that would explain that indeed you have, which I show here. Well, not very well probably. But there are many modes for electron-positron annihilation. You see, they can annihilate each other in very different ways. But that's sort of, I think it. I think these theories should be worked out, and I will try to do that maybe. I said, take into account maybe that not always we have a situation in which the electron and the positron dance around each other and form a positronium. The decay, the mean lifetime of positronium varies. Sometimes an electron and a positron seem to, annihilate each other immediately. There's even no dancing around. And then indeed sort of a theory where, you have these various decayed modes. Said, is it a W plus, is it W minus here? Or do we have like one virtual particle here, a Z0 boson, which kind of combines both, and then here we have a real photon, which is only a field. A photon, a light particle, is different from a matter particle, I always say, because matter particles, and this is why I have a problem with calling them bosons, is photons do not carry charge, and so there's a field. A field is like, think of a force moving in time, but without a charge to act upon. It's only when the photon is going to meet a real electron that we can talk about real energy. So people often talk about field energy, and I do that too. But it's kind of a confusing term. I prefer to talk about potential. And potential is not exactly the same as potential energy. Again, energy is, there's a formula for a field. A field is the force per unit charge. That's a field, magnetic field, or for a electric field. For a magnetic field, it's a bit more complicated because your force formula is quite different. That's basically what I wanted to say. I'm gonna pause a moment because I wanted to add something, but think I forgot to say something. Bum bum bum. No, I can't recall it now. There's a point I'm missing, but I might come back to it. Let me go to my conclusions. I wanted to make this presentation rather short anyway. Said you have a lot of modes for you know, an electron and a positron, you know, annihilating each other. Electron, positron. So this is usually in sort of lower energies. The electrons don't move so fast. They just happen to meet each other at lower speeds. They will decay, well, annihilate each other into two gamma rays in opposite direction, almost opposite direction. This is also something funny and kind of, it's not quite opposite. And that's where I'm thinking also that probably, you know, well, the direction basically no. The direction, if there's a small, you know, the difference in the angle might absorb some of, you know, the positron might have had some more energy, kinetic energy than the electron, or vice versa. And that's where maybe, you know, if you have the conservation of linear momentum, that the angles in which these two, I will call them virtual photons, exactly because they disintegrate again into an electron-positron. So this is what I refer to in my papers as a bit of sloppy accounting. This gives the idea that, you know, photons, light particles, matter particles, you know, fields become charges and charges become fields and vanish. I think that's what Richard Feynman referred to when he said, you know, there's a lot of cargo cult science in popular physics, but I think there's maybe also a lot of cargo cult science in more serious physics, in academic physics. So I said these photons apparently decay into you know, an A plus, and that's why I said, like, for me these are virtual photons, and virtual photons aren't real photons. They aren't photons. They are not just, you know, an oscillating electric field with at the same time a magnetic field at a 90-degree angle with it. That's how we imagine, you know, a photon to propagate, or electromagnetic radiation to propagate, as I explained in my last video. No, they're probably more virtual particles, but special ones, because they do travel at the speed of light. Yes, that's where I remember what I wanted to show when we talk about these virtual particles. Is in the Zitterbeweging model, and this is a figure, I hope I have it still. No, I must have erased the page. Let me draw it here then. If we have this Zitterbeweging current, right? So this is the size of an electron, which is 2 times 2.80 femtometer. So that's 2 times AH divided by the mass of the electron times C. That goes around, you know, at the speed of light. When our electron here, or our positron, you know, starts moving in you know, some lateral direction, what happens basically is nothing can travel faster than the speed of light. So what we must have is that the radius becomes a bit smaller, you know, for, let's say, 0.8 times C. Why? Because some of the tangential speed is now, you know, we have an x component probably, Vx, and then so the Vy, and sorry, the Vy and the Vz. You know, if it's only these, if this is 0, then we know that Vy square plus Vz square should be equal to the square root of C is C. So their speed, C, when in orbital motion, well, when this is no longer 0, well, then this equation doesn't hold, and it means that the components in the y direction, if we have this the y, and then this is the Z. Oh, this is not a very regular right-handed frame. Or maybe it is. No, it's not. It's a left-handed frame, so I should put Z here and Y there. In any case, it will have a smaller, and we explained it also in previous lectures that you can work that out. You can have a wave function representation now, A times E, and then phase argument, the angle, and the imaginary unit as the rotation operator. A will become smaller. So that explains a relativistic length contraction, I think. And there will also be, this phase angle is equal to the frequency of rotation on the orbital frequency times t. That also we will see a relativistic length contraction, and we will have to distinguish between what we observe and for the electron, its position x, and its reference frame is always 0. And, I explained that. I'm not going to go into detail. The thing is, if things go faster and faster, let me take another color. Let's suppose it accelerates from, a linear velocity of 0, and then, it goes faster and faster and faster and faster. And it reaches the speed of light. All of its orbital motion will be gone. All of its energy will be in, its linear velocity c. And this is the big question, which I cannot answer, because an electron has a non-zero rest mass. Can it really reach c, or is the Zitterbewegung charge, which basically has no orbital motion? Maybe it has some spin, because you can imagine if it goes around, even if it stays stationary, is that it actually in one rotation, it will actually rotate around its own axis one time. So maybe there's a little bit energy left it spins around. It doesn't have a big orbital motion, but this Zitterbewegung charge, whose radius is the classical electron radius alpha. I explained that too. So that's about 0. That's the femtometer. That's actually 0.28 femtometer, and this is, I'm sorry, 0.386 picometer. Electrons are quite large as compared to protons. So it's in the picometer scale, and 0.38. So that's 2 times 3,860 femtometer. About 1,000 times larger than a proton, and 1 over alpha times larger than that, which is about 136, I think. 137, yeah, 1 over alpha. So this is my theory, actually, is that we can imagine that the electron has a sort of or the Zitterbewegung charge has a sort of zero energy state, looked at from its own rest frame, from its own frame where it is not moving. But the Zitterbewegung charge, there was Schrödinger's hypothesis, it's not zittering around. If there is a secondary motion, it's confined to a very simple spin of what we think of as probably a solid and very small sphere of charge. And so that when it has a zero energy state, we can think of if this was an electron-positron could also sort of accelerate at the speed of light, and also have a zero energy state, but it comes from if you call this a positive energy state and this a negative energy state. So they could actually sit on top of each other. This is really very speculative what I'm telling you, but to me it makes kind of sense. We could have this one and this one sitting on top of each other and speeding at the speed of light. Or what would be possible, that would be then a Z0 boson, which is like a virtual photon. Actually, a neutral combination of two Zitterbewegung charges, core, like the hard core of an electron and a positron, sitting right on top of each other and moving at the speed of light. Alternatively, we could have also, depending, the positive charge going almost at the speed of light, because It doesn't have any orbital motion anymore. It only has its what we call, in the context of an atom, intrinsic angular momentum of an electron. When you have a proton, an electron goes around in all kinds of weird trajectories. This motion, we will call that the normal angular momentum, but it also spins around its own axis. But here we're talking about this electron. So it has intrinsic angular momentum, we call that. And so here we would have a different intrinsic angular momentum. The intrinsic angular momentum of, it's like a fractal structure of the charge inside the electron that is in some orbit around an atom. So that's the thing I wanted to add to sort of show that and I'm going to conclude my lecture here, is when you look at all these decade modes, what strikes me is that we have a lot of virtual particles here. Things you can't see. Z bosons. I looked at the experiments and W plus bosons here. I think what we see here, or what we assume to be here, I said that might be a Z0 boson. So I think there's some proof for, and all the experiments for which Nobel Prizes were given to Weinberg and Salam, his theory, and the experimenters later who proved his theory. I think these bosons and all that, yeah, fine. We've sort of observed these, I would say, indirectly, but still, it's a very it's an indirect observation that speaks to me. In contrast, Higgs bosons, quarks, gluons, what they say about quarks and gluons is that there's confinement, so you can never really see them. And when you go to the CERN experiments and you read the press releases and the studies, they will say, well, quarks must exist because we have several theories in the standard model. There's not one standard model, but these sort of, the quark hypothesis is the theory that, is preferred above all the others to a degree of 98%, 95%, 90%. I don't know, I talk about this in the lectures, you will think I'm joking, but it's really true. Go to the papers, and the quark hypothesis is still a hypothesis. No one has directly observed, in these experiments, quarks, because of confinement. We can't see them. They stay together, and if they sort of separate in this virtual space, if gluons ferry around, I don't know what color charge. What is a color charge? I think they ferry around momentum or energy, which is not needed. It's like a new ether theory. But all these things, in the end, disintegrate back into, stable particles, and basically, where they came from, E plus minus, but, inside of another hydrogen atom or as a free positron, whereas, here we got them out from firing protons at an iridium stick, and then neutrons, and firing them in a bubble chamber filled with hydrogen and heavy neon. For me, these are all, I would say, virtual particles, especially those ones. Quarks, I said, I think really that's sort of a figment of the mind, some temporary state. And this is where I want to show you that, and this is there I'm going to conclude, is that, the elementary particles, I think in a classical approach, when you believe the Zitterbuoy, yeah, we have fermions and we have bosons. I agree with that distinction, but I would call it more light particles. And light particles, what distinguish them, they're only fields. They do not carry charge. So these are fields, photons, or neutrinos in various generations. Neutrinos, I said protons, I refer to my previous lecture. I think of protons as also a ring current, but a ring current that has like a third mode of oscillation. So the ring current as a whole oscillates like back and forth, or this spins around. It's more like a spherical ring current, I would say. And so when you mess around with protons and some excess energy needs to go somewhere, I think that will be a neutrino, which is like, photon is a linear thing, and
The electric field vector goes like this, the magnetic likewise. This is two-dimensional. These neutrinos, because the proton has a three-dimensional structure, might actually also have, you know, a field going back and forth while it's of course moving. And this is, I think, the discussion about the rest mass of a neutrino. Does it have rest mass? In theory, no. In reality, you know, this third dimension, because it's a three-dimensional oscillation of electromagnetic field, there's only one force for me. It might have, you know, may appear to have some rest mass because of that motion in the direction of, well, motion. So bosons, for me, there are only photons. And this is then the funny thing. Neutrinos actually here are classified as leptons. I think they must come in this category, and they're light particles. But then we have electrons, and then I think in the classical, you know, the standard model. Sorry, in my there's no place for quarks. We have protons, and of course the antimatter counterparts. And now we can make composite things. You know, neutrons. You can see them as a they're only stable inside of the nucleus. So I'm thinking of you know, the proton is a ring current, then and there's another proton here. You see that immediately if two protons can't be together in one nucleus unless there's sort of a glue. That's probably where gluons come from, and that's the neutron. And the neutron, we can see it as a neutral combination of positive and negative charge. And you will say you're completely losing it now, but I'm not actually, because if you go to my papers, I write, and it's a quite popular paper of mine, on pair creation and annihilation, where I basically say that it's like a nuclear process. When you look at all these reactions, we forget that these neutrino beams or proton beams are fired at nuclei, and we are indeed doing sloppy accounting. Where what happens to the neutron when sort of a proton gets torn out of a nucleus? We don't keep track of, we can't, it's technically impossible probably, of what happened to that nucleus. Perhaps it lost a neutron as well. And that's where I do believe that with better accounting, we might be able to prove that there is not only global charge conservation, but also local charge conservation when indeed you have this ring current model, when you believe in it like I do. So, but I'm gonna conclude now. But this is basically, you know, my classical theory. You will say, should we? Why are you promoting it? I'm promoting it actually to save probably you time, and then when you, I mean, you know, there's many people like me who sort of want to understand all these theories and say, okay, where are we now in terms of, you know, grand unified theory? What is this weak force? What is this strong force? I said, for me, a weak force implies the idea of a charge, and we only have the electric charge. So there's only an electromagnetic force and nuclear force. I can understand. I explained that in my papers why they thought there might be a different force inside of a nucleus. Because the force field appears to be asymmetric. It dies out after h divided by m proton mass divided by c, which is about 0.21 femtometer. So, but you can, and that's what I do in my papers, you can explain that by, you know, this theory, which basically says, you know, we have orbiting charges with a dipole moment, an electric dipole moment in a neutron, and a magnetic dipole moment for a proton. And you know, at these short ranges, and because the velocities are so high, these are enormous forces, and the field is asymmetric because, you know, yeah, dipole fields happen to be asymmetric in classical electromagnetic theory. And so for I don't think there's a nuclear force. If there is one, we should urgently invent a unit for it, the Einstein or the Dirac, and find that nuclear charge. I don't think it's the color charge. If it is, then yeah, call it a nuclear charge, and define very clearly what the force is on this charge and how it works. Is there also like two components, an electric and a magnetic one, or are there more? So that's not happening with this quark gluon theory. So I don't pay much attention to it. And for the weak force, I said, a force keeps things together or pushes them apart. Things that disintegrate, that's not a force pulling them apart. That's basically because they're an unstable configuration of charge. And what is unstable about it? Well, it does not respect the Planck-Einstein, the various frequency. This is a simplified, of all the oscillations that you might have going on in something, a big oscillation with a rotation within a rotation, which then explains these weird symmetries, 720 degree symmetries or other ones. But it's slightly off, the oscillation, I would say, and that's where this thing then falls apart. Just like into more stable system components, I would say. This is a unstable system, and it's going to fall apart in stable systems or also unstable systems. But until you get something stable, a real stable elementary particle. I said all that second generation stuff, which is not shown here. These are unstable particles. These are composite particles, and they're off, so they're not elementary. And this is where I think the standard model is philosophically unsound, because it doesn't make that ontological distinction between stable particles and unstable particles, and composite particles and elementary particles. Everything that happens in high energy physics is per definition the study of unstable disequilibrium states, complex systems that disintegrate, as mentioned, into stable things. So I think I've talked for too long. But I'm happy that I sort of could conclude what I was talking about. Yeah, maybe I can show this one. This is another way of representing it. So I said these Z and W plus minus bosons, yes, but don't call them bosons, call them virtual particles. Because bosons, I would reserve that for photons and neutrinos. Where are they? Here. These are all light particles. Electron, yeah, and sort of muon tau, I said these are unstable, heavier versions of the electron. This thing here, quark, I don't know. I wanted to scrap it, but protons, neutrons, what a neutron is, thinking of them as ring currents. A neutron as sort of the glue between protons when a nucleus becomes more complicated, heavier. I think that will do. Gluon, we have the electromagnetic force keeping, protons and neutrons together, protons as a ring current, and protons and neutrons and protons. So no need for gluons and color charges. Higgs, a mass generating mechanism. The ring current model has a mass generating mechanism. I said it defines or looks at mass as charge in motion, and the mass as it appears at the macro scale, an inertia to a change in the state of motion of a particle or a wavicle is just the equivalent mass of the energy in that charged oscillation. So the mass generation mechanism is implicit in that. I think that's consistent with 2018-19 revision of SI units. I also think that's consistent with the ideas of John Archibald Wheeler on sort of a mass without mass model. He was also thinking a charge without charge model, which standard model actually has, because charge can become a field, and a field can become a charge. So we have a theory says, yeah, charge is not essential. For me, charge is essential and fields are essential. Charges generate fields, and the fields explain the motion of the charge. And the ring current model is beautiful in that way, that we have that electromagnetic field. It's like a superconducting loop, really. What you see at the macro scale in supercooled materials, we can create a magnetic field, and then we will have a current, and then we stop the magnetic field, and then the lens said, okay, now we will have a current that will generate the magnetic field that keeps the current, that was generated by the original magnetic field in place. So you can have a superconducting loop at a microscale, which generates a magnetic field which keeps the current going. So it's a perpetuum mobile model. It doesn't radiate its energy out. Superconducting currents at the macro scale, they are Cooper pairs, because then you have the issue of spin, of course. So there's basically Cooper pairs at the macro scale. At the micro scale, an electron of a proton itself, we don't need a pair of charges. Sorry, this should be spin up and down. An electron up and spin down for a superconducting loop. My pen is not doing it anymore. Down. Okay. In any case, I've talked too long, and probably I come across as a little bit confused. I'm not. I think I know what I'm talking about. All this makes sense to me, and I will leave it at that, and I will upload it, and I will upload it with this as a closing image, and that I will maybe alert my opponent on ResearchGate on my interpretation of what happens here on this picture. So for me, what is traveling here is a virtual photon, you might say, or a virtual particle, or an intermediate vector boson. I don't care what you call it, but it carries the charge that originates here as an electron and a positron separate from each other because of a magnetic field that pushes them in separate directions. The thing with this is also, for an electron and a positron to go in the direction, there must be some serious kinetic energy. Otherwise, they would just do this, right? If there was no kinetic energy. So I'm thinking the kinetic energy, does a photon have enough kinetic energy? He says this photon has an energy of more than 1.022 mega electron volt, which is 2 times the energy of an electron at rest and a positron at rest. So that's enough, but that's not enough to give them this kinetic energy. I said you have highly kinetic particles coming in here, and so the curvature of these things is looks impressive, but otherwise we would really have something more like this. They would stay on the spot if this thing would not be much more, I wouldn't say massive, but wouldn't have much more energy. And that's it. That's my sense making exercise of this beautiful science, quantum mechanics, mathematics. That brings it all a bit together. So that's my entertainment, and I think you probably didn't sit through the whole video, but if you did, congratulations. And then if you did, then I hope it's good entertainment for you as well. I'm gonna leave it at that, and I wish you a very, very nice evening. I see I'm exactly at 1 hour, which is kind of great for a last concluding lecture, I think, because I have a different day job, and